In this video, I am going to discuss about the design of BCD to Excess3 code converter. First, let's see about BCD code, or otherwise we can call 8421 code. BCD code is an abbreviation of binary coded decimal. That is a coding scheme relating decimal and binary numbers. And this BCD is a type of binary code is used to represent a given decimal number in an equivalent binary form. The BCD equivalent of a decimal number is returned by replacing each decimal digit in an integer and fractional parts with its 4-bit binary equivalent. In general, BCD codes are also called 8421 code. This is because 8, 4, 2 and 1 are the weight of the 4 bits of the BCD code. Next, BCD code. How we can represent the BCD code? In this code, decimal digits 0 to 9 are represented by their binary equivalents using 4 bits individually. For example, the decimal number 429 is expressed in BCD form. Each decimal number is represented by equivalent 4-bit binary number. So 9 is represented by 1004 and 2 is represented by 0010 and 4 is represented by 0100. So the lowest BCD digit is 0 and the highest BCD digit is 9. So this is the truth table for decimal digit and the BCD equivalent. So the 0 to 9 combinations are used for the BCD code. So in this BCD code, 10 to 15, the total 6 combinations are there. This 10 to 15 combinations are the invalid code. The Excess3 code is represented as Excess3 code. It is a non-weighted and self-complementary code. This code is mainly used for arithmetic operations and it resolves the deficiencies encountered in the BCD code. Generally, the Excess3 code is obtained by adding 3 to each decimal digit. And then we write the 4-bit binary number for each digit of the decimal number. Excess3 code have self-complementary property. That means a binary code is a code which is always complemented in itself. How we can obtain self-complementary property is first we have to take one's complement of the given number. For example, we are taken the decimal 5 in Excess3. Now we are taking one's complement of this number, that is 0111, which is the Excess3 code of 9's complement of 5. That is 9 minus 5 is 4. So if you are taking one's complement of any number, that will give in 9's complement of that number. This property is called self-complementary property. Then the Excess3 code has 6 invalid states. The 6 invalid states are 0, 1, 2, 13, 14 and 15. This code is very much useful for performing subtraction. This is the truth table for BCD to Excess3 code converter. The BCD inputs are represented as A, B, C, D. And the Excess3 outputs are represented as W, X, Y and Z. Now the BCD is a 4-bit code and it can be represented from 0 to 9 combinations. In the BCD, 10 to 15 combinations are considered as don't care. These don't care combinations are used in the KMAP to simplify the expressions. Now from the truth table we are getting the SOP term, sum of min terms for all the 4 outputs W, X, Y and Z. This is the sum of product expressions for logical output W, and here we are having don't care terms as well as the min terms, and we are placing the min terms and don't care terms in the 4 variable K map. Now we are grouping into these 2 ones into 8 cells grouping, and these 3 ones we are grouping into 2 4 cell groupings. Now we are writing the logical expressions for this grouping. The common output term is A. Then for this green color grouping, the common term between these two is B, and the common between these two term is D. And for red color grouping, the common between these two is B, and the common between these two is D. This is the sum of min term expressions for output X. Now we are placing the sum of min terms and don't care in the K map, and we are grouping this one with this don't care. So 2 cell grouping is possible here, and this one and this 9 and 1 3 is combined into one 4 cell grouping, and this 10 11 and 3 2 is combined into another 4 cell grouping. Now we are writing the logical expression for this combination. Here the common between these two is B, and here C bar D bar. And for this blue color grouping, the common between these two is B bar, and here the common between these two is D. And for the green cell grouping, the common between these two is C, and the common between these two is B bar. This is the logical expression for output X. And this is the sum of min term expression for output Y. Now we are placing ones to the cells, and these 3 ones are grouped with along with the don't care. So 4 cell grouping we got it, and similarly other 4 cell grouping we made it like this. Now the logical expression for this cell grouping is C bar D bar, and here CD. This is the logical expression for output Z. So we are writing the min terms into the table, and we are combined into one 8 cell grouping. These 4 cells and these 4 cells are adjacent each other, so we are grouping into single cell. So the common between these this cell and this cell is D bar. So Z is equal to D bar. We need more number of gates to draw the diagram. So to reduce the number of gates, we are simplifying the logical expressions by using Boolean algebras. Then we got the logical expressions this way. Now we are drawn the logical diagram with less number of gates compared with previous implementations. Thank you.